This is problem 15-56. A 5 kilogram particle slides on a frictionless horizontal surface. At some point in its path, the velocity of the particle is 96 I hat plus 72 j hat meters per second squared, or meters per second. 25 seconds later, the velocity of the particle has changed to v2 equal to 36 I hat minus 12 j hat meters per second. Determine the magnitude and direction of the constant force required to produce this change in motion. Okay, so this is a particle, meaning the object technically has no shape, or we just don't care about its shape in this context, right? And then we have a velocity with a certain vector, and then a second velocity with a different vector. And both the I hat and j hat components have changed. Okay, so in a way, you can kind of pick up that this object has changed speed and it's turned as well. So it's going to have curvilinear motion, which is the name of this section. Okay, and there's going to be a slightly interesting story about how the accelerations work and things like that. So let's take a look at the math for this problem. So first, let's draw something that is going to represent this particle. And a circle is a good shape because we don't care about the shape. That will be in chapter 16. And we just need to know how external forces are causing this object to translate. We don't care about rotation. Okay, so the mass is 5 kilograms. And on a frictionless horizontal surface, okay, so I guess that it would be sitting on some surface like this. At some point in its path, the velocity of the particle is v1, and we got the vector. So v1 as a vector is equal to 96 I hat plus 72 j, let me try that again, j hat. Okay. And then there's the second velocity, v2, is 36 I hat minus 12 j hat. Okay, so determine the magnitude and direction of the constant force required to produce this change in motion. So they're saying there's a force in some direction applied to the particle all the time. All right, so I have a feeling that with the way that this is presented, the horizontal surface is actually below us. We are looking down at this particle, and the particle is allowed to slide. I'll do this in green. The particle is allowed to slide in any direction at once. So we actually have a bird's eye view. We're looking down at the particle sitting on a surface. And therefore, that means that there is going to be some force, we can call this F or whatever, at some angle all the time on this particle. But the particle has already been moving at the velocity 1 direction. So to the right a little more than it is moving up. So the velocity has a component to the right 96 and up 72, which then means that the velocity is something roughly in that direction. All right. To not create clutter, I'm going to erase these arrows, but I just want to show you that that means that this diagonal arrow is basically the already moving direction. Now, look at what the velocity is later. It is moving, I'll draw in let's do blue. There's going to be some velocity in the x, but then there's going to be a small velocity in the y. So the object is going to change to this direction. Right, so the blue is going to be the new velocity later on. So that definitely means that this arrow that I've drawn is for the force that's creating this motion. And real quick, just so we don't confuse the forces and the motions, I'll draw this arrow green. Okay, so the green motion is the initial velocity, and the blue arrow is the final velocity. So I've drawn a force arrow here that doesn't seem to make sense. However, doesn't really matter because we don't know what the values will be. And if we assume the arrow to be going up and to the right, if the force is actually going down and to the left, for example, then that means that we're just going to get negative answers. Okay, so drawing our arrow to the right for positive and up for the positive as well as an assumption will allow us to get answers later on that are going to make sense to show us that if the arrow is pointed down at all or to the left at all, we'll get negative numbers. All right, so we have a free body diagram. Now let's make our equations. So first, let's start with the sum of the forces in the x. All right, and that's going to be the force cosine theta equal to the mass, which is 5 kilograms, times the acceleration only in the x direction. Okay, and then sum of the forces in the y is going to be the force sine whatever theta is going to be equal to 5, the acceleration in the y. All right, so we have f is an unknown, theta is an unknown, ax is an unknown, ay is an unknown. Oh, that's 4 unknowns, and we only have 2 equations, so we need at least 2 more. All right, so we are going to have to figure out some way to make 2 more equations. Well, there's a trick. If we solve for the accelerations in the x and the acceleration in the y, first, we will get 0.2, not p, as a different variable that I use, okay? So f cosine theta, and then we solve for 0.2 f sine theta, okay? Then what do? We can integrate our accelerations. So the velocity of x is equal to 0.2 ft cosine theta plus some c, and then the velocity in the y is equal to 0.2 ft sine theta plus another c. So there's a c1 and a c2. All right, or a cx and a cy. Doesn't matter. Okay. So what are these c values? Well, they are going to be the initial velocities. Which initial velocities? The initial velocity in the x and the initial velocity in the y. Where do we get those numbers? Back up here. These 2 values, 96 and 72, are the initial velocities of the problem in those 2 directions. So that means that cx is equal to 96 and cy is equal to 72. Okay, well, we still have f, we still have theta, but we have the velocities. So we added 2, we may have gotten 2 new equations because these don't count. These are just rearrangements. But we unfortunately have vx and vy as unknowns as well. So, what do? Well, we do know, though, that there are velocities here for x and y later that we are aware of. Okay, so if we plug those velocities in, we can find out what forces and theta angles we would need in order to satisfy those final values. So that means that we can make these equations equal to the 36 and the negative 12. And now we have a force, but we do have a t. So when is this happening is the question. All right, we know that we have velocities later, but do we know when we have these velocities? Well, the number is not written in the problem, but it is stated in the problem. And you might miss it if you're not paying attention. The third sentence says 25 seconds later with words. So be very careful. Make sure that you have basically a initial time equals 0, but a final time equal to 25 seconds. And then that means that t here and here is equal to 25. Okay, so that is when we have these 2 velocities. So the t's are not unknowns. They're equal to 25, both each. And then that leaves us with only unknowns f and theta, ax and ay. That's 4 equations, 4 unknowns. We can solve for this problem. So The final answers are theta is equal to negative 125.5 degrees, or you could write it as 54.5 degrees below the negative x-axis. Okay, and then our force required is 20.6 newtons, all right? And the angle is then that theta that we found, 54.5 degrees. All right, that is the answer to the question. You don't actually need to find the ax and ay, because when we get to this version of the equations, ax and ay disappear, and we actually do know the vx and vy. We found it over there. There are actually only two equations, two unknowns, because we also know that the t is equal to 25. So understand, you don't have to come over here and solve with these two equations. We used these two equations, solved for acceleration, and then integrated and got this new version that had forms of the information that we had known values for. And therefore, we were able to use those two equations to solve for the two leftover unknowns that are the actual things that the question wanted us to find.